All right, today we're going to begin our first classification model. We'll talk about logistic regression. This section is going to be logistic regression, but I think the main focus of here, I mean, I will get into the algorithm of logistic regression, but I also wanted to talk about how you evaluate all classification models. So I think that's going to be more of the main takeaway from this. Logistic regression, I'm going to go over how it works. I also will send out resources that explain it more in depth if logistic regression ends up being a model that you want to really hone in on. But I will share just enough for like a high level understanding. Before I get into logistic regression, receive some questions regarding other parts of the course. So I want to go through those first. First of all, Melody had a question regarding the two dents. So wanted to talk about what that is. That's actually a really interesting like data question. Where did it go? Oh, here it is. And so here you see that, let me make this a little bigger so y'all can see. Here you see that there was some one hot encoding done, fitting and transforming the your X data, your feature set. One hot encoding done is basically you're doing your categorical variables, but all at once. So if you had like multiple columns of categories, it will do the get dummies all at once for you. Excuse me. And then what you have to do once you've one hot encoded, you actually have to add this toDense function. This is actually really interesting. It's actually pretty interesting from like a memory perspective. So if you imagine when you do a one hot encoding, you end up with basically just ones and zeros. So imagine if this was mostly categorical, you end up with ones and zeros, majority zeros. And so because of that, I believe it's within NumPy, but NumPy has regular matrices, but also sparse matrices. So regular matrices is what we know as, when we set up the array in 2 dimensions. We saw what those looked like in linear algebra and some other examples. And a regular matrix is considered like the dense matrix. So what we're doing here is we're converting whatever this other data type is, which I'll talk about shortly, into a dense matrix where you can actually see the 2D array of your numbers. Doing something like a one hot encoding where you end up with mostly 0 values, they actually store it as this other data type known as a sparse matrix. So a sparse matrix is actually a lot more efficient memory-wise, because what a sparse matrix does is it doesn't store like, your entire 2D array of like a bunch of zeros and ones and all your other values. It actually only stores the non-zero values. So I believe one hot encoding or several other of the cycler methods, it recognizes when something is going to be relatively sparse. Sparse meaning has mostly zeros. So it only saves like the position and the value of non-zero values in the matrix. So it saves a lot on memory storage. And one downside is that sparse matrices cannot be read into data frames directly, which is why, from the sparse matrix, I believe it's actually like, if I'm not wrong, it's similar to a list of tuples where each tuple is like which row, which column, what's the value, or something very similar to that. So all this like toDense function is doing is converting that, like you can sort of think of it as like coordinates and value, into a dense matrix that can be more directly read into a data frame. Any questions about that? Awesome. So that's toDense, and basically what we've learned is that there's sparse matrices and then there's dense matrix. All right, the next thing I want to talk about was Ali had a question about .reshape, which is another NumPy question. Reshape is an interesting one. Let me just make like a bunch of empty cells to show what this is. Maybe not here. Maybe we'll do it up at the top. There we go. All right, so if I import NumPy as NP and I have a NumPy array of, for example, 1, 2, 3, 4, 5, 6, this is going to show up as a 1D array. And so the purpose of Reshape, typically in the examples that you'll see, you're going to use Reshape for converting 1-dimension arrays into 2-dimension arrays. Reshape is actually pretty neat because it actually can reshape any array into any other shape as long as you have the same number of values, and I'll sort of show how that works. So let's call this test for now. So we have this test array. If we look at test.shape, it is 6, nothing. Note that that is different from 6, 1. This is a one-dimensional array. When you do a reshape, and I always mix up the order, to be honest, either -1, 1, or the other way around. So it would be the other way around. 1, -1. The difference between this and the difference between test and test.reshape, you take a look at the shape here, this is 1, 6. And if you reshape it the other way around, it'll give you 6, 1. I think what throws some people off is the -1. -1, if you ever have a -1 as an argument in your reshape, what it will do is it will coerce whatever other dimension you have, and then the -1 will just, you know, fit to fill the other dimensions up. So as you can see here, we're setting that we would have 1 column, and then -1 will be like, all right, however many values we have, we'll coerce it to have 1 column. Just really quickly, what other things reshape can do is, these are 6 values, so I know that 2, 3 will work. Reshape works like that. The way, and probably the use case in which you will use reshape the most is when you're, I'm guessing, using your predict functions. So when you're doing model.predict, and a couple of you actually did this, created prediction functions for your housing prices. When you've trained a scikit-learn model, and let's say you want to feed it in like random values of like bedrooms, bathrooms, square foot to predict the price of a house, you actually do end up needing to reshape your values. So let's say you get something like, and I'm not actually gonna run this, but square foot, bedrooms, bathrooms, etc. When you have this, it first sees it as a one-dimensional array. So the same as this test.shape, one-dimensional array. And scikit-learn usually, I mean, it's usually for the benefit of being able to run it it's to make multiple predictions. It actually requires a 2D array. So that's why you have to throw in that dot reshape to just make it such that, you know, instead of a 1D array, you have it as a 2D array. So I believe it's 1, -1. So it feeds it in like that. Another way, instead of doing reshape, that some people use to like get around that, is you just throw in another set of square brackets around that. So it sees that, all right, this is the input for a single data point. Hopefully that clarified. Yeah, the main use case, and I think this is where people see it the most, it's in using your prediction function.
Thank you.
You're welcome. Yeah, sometimes in your error message, they actually do tell you to do dot reshape if it, especially in the predict function. I know that one definitely will tell you to do a reshape. Cool. Questions about this? All right. The last thing I wanted to talk about before we get into logistic regression was a question from Sarah, and it's about, with linear regression, when we're doing polynomial transforms, is it still a linear model? And the answer is overall yes. So with a linear regression, and let me see if I can pull up our old study group notes, and maybe I have that somewhere. Let's see. Hopefully it's in, we have something here that we can look at. But yeah, in a linear regression, the linear part of the linear regression comes with the coefficients. So the coefficients that turn up on our on that printout with the stats models. That's what the linear part is. I hope I have an equation here. No, I don't. But it is linear in its coefficients. It wouldn't be linear if the best model, for example, had us multiply coefficients with each other, or if our coefficient had to be squared. And because the way a linear model works, you're actually just solving for a bunch of constants to multiply each variable by. The polynomial features are squaring the variable itself. So it's not like you are inputting your variables and then with your coefficients, you're messing with that. You're more of like, you have your input, you know how to transform your input into polynomial features that will then be solved with linear coefficients. I don't know if that was helpful.
So it's linear because you're like adding them together?
Yeah.
Like
That's right.
all the different coefficients and values you have, you're adding them together. But if we were like multiplying them together,
Yeah.
then that would be a representation of a different kind of
That's right.
model.
That's right. I think overall, because each feature has a linear coefficient, or like each feature is still multiplied by a constant, even though, you know, with your input features, you might be multiplying some of them together. Let's say you have feature A and feature B, you multiply them together, but in your model, that is still multiplied by some constant determined by your model.
Okay. Okay, that makes sense.
Okay, I'm glad. Before I get into logistic regression, any other questions? Cool.
Can I
All right,
ask one more really
oh,
quick? Sorry.
absolutely. Yeah,
Just
absolutely.
really quickly, when adding interactions, I think there was one that we like in chapter 24 where we have to do a lab with that. Do you have to drop the first two like the two separate features by themselves, or if you're doing like a lasso regression, will it take care of that multicollinearity?
So in lasso and ridge, actually, they will take care of the multicollinearity for you.
Okay.
In a regular linear regression, it actually does depend, because sometimes when you're multiplying two variables together, especially if they're like not scaled, you will have to actually check for multicollinearity between the two individual variables and the interacted variable.
Right. Okay. But
Yeah,
if you're doing like a lasso or a ridge regression, it should take care of that multicollinearity for you.
Yeah, that's right.
Okay.
Awesome. Any final questions? All right. So to start logistic regression, and this kind of kickstarts our next like big topic of classification models, I wanted to do like a quick zoom out and just to see like where in the landscape of things we are currently. So this is just one of many diagrams that summarize like the whole field of machine learning. So in the center, machine learning, the main three branches out of machine learning are supervised, unsupervised, and reinforcement learning. For this course, we will actually be talking about both supervised and unsupervised learning. Reinforcement learning, we actually do not touch at all. It is extremely advanced. I personally have not had any experience with reinforcement learning either. It's basically, reinforcement learning is what trained the computer to play chess, or play like alpha, play Go. I think that's the game that it played. So that is that. Like PhD level, like data scientists work on that stuff. So I personally don't have experience with that either. So the two main branches that we will be looking at are supervised and unsupervised learning. What we've been doing so far with linear regression is supervised learning. And I will talk about the differences between the two in a little bit as well. Supervised learning, you have two main fields, classification and regression. Regression, we've done that. Anything that you're predicting a continuous variable is a regression problem. Although we will be talking about classification models in this coming couple of weeks, a lot of these classification models do have regression counterparts. So if you ever end up doing a regression again, perhaps for your capstone, you could consider some of these other regression models instead of just doing your linear regression. I think it'll make a lot of your lives easier. You don't have to worry about assumptions and things like that. And as we get to those models, I will always mention like which ones have regression counterparts. So regression, we're familiar with possible problems predicting the price of a house like we did already. Here you have popularity prediction, market forecasting is a very popular one. Life expectancy, I think that was one of the projects that I had linked to see like the PowerPoint presentation for your last project guidelines. So we're familiar with regression. Aside from regression, there's classification. So classification, the main difference is what we're predicting is not continuous. We're predicting categories, we're predicting classes, we're predicting binary, can be more than binary, just things that are not continuous. It can be, it can range from things like, all right, am I going to like this restaurant on a scale from 1 to 5? Like pretty common problem that people solve. That, all right, based on this review, how many stars would you rate this restaurant? And that could actually be a classification problem. Other things that we will talk about, we will actually talk about image classification next phase. Identity fraud detection. There are quite a few fraud data sets that are very popular. I'm actually going to send out, I'm not going to send out a fraud data set. I'm going to send out a credit card default data set. So kind of in the same realm, but fraud detection is very, very popular right now. If you're interested in like being finance adjacent, a lot of fraud detection work. Diagnostics, maybe you want to see if something is working or not, or sound or not. Classification models can help you with that. Customer retention. One of the data sets for the project that you can choose from is on customer retention, just based on like the activity of a customer. Are they likely to continue using your product or service? So any questions about the distinction between classification and regression? The main thing is really what is being predicted, continuous or classes. So to re-zoom out again, besides supervised learning, we have unsupervised learning. And these two topics of clustering and dimensionality reduction, we actually will talk about both of these in the next phase. The main difference between supervised learning and unsupervised learning is supervised learning has labels, unsupervised learning does not. What I mean by that is when we were doing regression and we were trying to create a model to predict houses, we had these actual values of the houses that we could compare our model results to, so we know how well our model is doing. So we could always, like, calculate RMSE and just see how far away our predictions are from our actual values. With classification, you'll see that our data sets will have often like zeros or ones to classify like binary classification problems. And you can, again, compare your results to these actual values. Compare your Y test to your Y predictions, just to see how your model is doing. So that's what I mean by labeled data. Unsupervised learning problems don't deal with labels at all. And we will get more in-depth into those topics in the next phase. But for example, clustering. A pretty common clustering problem is, I think in the sports industry currently, I don't know too much about sports, but I know in different sports, you have like different named positions, right? Like you have, I don't know, basketball, you have like a point guard, you have like a other, I don't know what else. But there's like this idea of, all right, these positions exist, but are there maybe better ways to group players? And so a clustering problem, and the way clustering works is you can actually tell an algorithm, all right, I want to create 3 new groups of players, and mathematically, based on like features about the player, maybe some of their stats and stuff like that, they will automatically group players based on where they are in like multidimensional space. And that's a clustering problem. And usually what you'll have to do then is you'll have to look into these groups of players and sort of determine, all right, can I create like new labels for these people, for these groups of players? And so that's sort of an example of how there are no labels, but your idea is to come up with your new labels, if that makes sense. And what you would tune in clustering is like sometimes, maybe you want to have 3 new groups of players, sometimes you want to have 4, maybe 5. Really just depending on the problem. But yeah, any clarification needed on the difference between supervised and unsupervised learning?
Most of the data in the real world are labeled or not?
That's a good question. It really depends on like the scale of which you're defining like what is data in the real world, I think. I think a lot of data sets are labeled. There are specific fields where it's less labeled data. Like for example, when you're doing things like, and we'll get to that as well, in natural language processing, and you want to do like sentiment analysis, a lot of like, you can't really label sentiment. So what you can do with clustering with language, you can actually cluster, like, for example, you want to look at and see, perhaps you're a restaurant. And as a restaurant, you're looking at your Google reviews and you want to figure out, okay, why do people hate my restaurant? What you can do is cluster your reviews, and through clustering, maybe you can pick out what are the main topics people are talking about. And then that could be helpful for you. And so that's kind of like unlabeled data. And actually what's pretty cool is with clustering, you can sort of create labels that you can then use in supervised learning. And if that sounds crazy right now, we'll get into that later. But yeah, any other questions about this? Cool. So that's just an overview of like where we are and where we're going. I think it's always good to like take a step back and like see where we're at. So with that, let's get into logistic regression, which is our very first classification model. I like to think of logistic regression as the classification counterpart to linear regression. Again, I won't go as in depth into logistic regression as I would like, but I'll send out a series of really good stat quiz videos. That is how I learned how logistic regression works. He has like a 4-part series that explains every little part of logistic regression. I'll send them out to you.
Quick question on that. I was watching him. He's using it as like a form of prediction, isn't he? Instead of classification. That's kind of how he described it.
That's a really good point, which I will also explain more later. But yes, he's kind of like predicting the probability of it being. So if you have classes 0 and 1, logistic regression is pretty much a probability curve of how likely is this point going to be 0 or 1. And with logistic regression and the way it works, you're actually setting a threshold of which to decide what probability cutoff would I round my values up to 1 or 0. That makes sense. And we'll talk about the transformation a little bit later as well. But yeah, you're kind of still predicting continuous, but you turn that continuous prediction into a classification, because your output before it gets to 0 and 1, the layer right before that, it's actually a list of probabilities, which is continuous. So yeah, that's a good clarification. But yeah, so logistic regression belongs to the class of predictive models called generalized linear models. Linear regression also belongs to this category of models. All of these models have 2 things in common. First, they define significant relationships between your independent and dependent variables. Like for example, with your coefficient printout of your linear regression, you can literally say, all right, a 1 unit increase in square foot will lead to a however much increase in my price. So it defines those relationships really clearly. And yeah, it indicates the strength of relationships. So you have those significance, you have that p-value, which denotes significance. And you have the actual magnitude of your coefficient, indicates the strength of your relationship. So the main difference from linear regression, again, I think they are very, very similar. But instead of doing, you're actually predicting a continuous value, you're predicting the probabilities associated with a success of a failure. So exactly what Stephen's question was about. Are you really predicting like a class, or are you really predicting like, a probability which will then be translated into a classification? So possible problems: is this email spam? What is the probability a citizen would vote Republican? Is this homeowner going to default? Anything that can be classified, usually you can throw into logistic regression. Before we get into like how the model is fit, just wanted to go over assumptions. They are actually slightly different from the linear regression assumptions. So first, because of what we're predicting, your dependent variable has to be binary for binary logistic regression. We'll also, actually the example that I have later on is not a binary problem. You can actually feed in multi-class problems into classification models as well. So the main thing is your dependent variable, what you're predicting, has to be non-continuous, has to be discrete. Only meaningful variables should be included. So actually very similar to linear regression, you'll get a p-value table for your logistic regression. And again, you want to get rid of your p-values that are above 0.05. Next, multicollinearity is still a thing to look out for. Oops. Multicollinearity is still a thing to look out for with logistic regression. So you do have to check for the same, are my features related to each other to prevent redundancy. Typically, if it's redundant, you might see a high p-value. The one that is different, and actually I think Joe put this question in the Slack channel. With our linear regression, we had the assumption of linearity, right? That each of our independent variables is linear related to our dependent variable. In this case, we're saying, all right, but our dependent variable is literally 0 or 1. What kind of linear relationship can we get there? So the independent variable should be linearly related to the log odds of your dependent variable. And I'll talk about what the log odds is in a little bit. But log odds is basically the formula of the log of y over 1 minus y. Finally, logistic regression also requires fairly large sample sizes. I will say, very likely with the data sets that you're going to use logistic regression for, they're not going to predict as well, which is why typically with classification models, you don't just try logistic regression, you try a lot of other models that we'll talk about next week. But yeah, logistic regression, if you want it to be very accurate, you usually require much larger sample sizes, again, because you have all of these assumptions to fulfill. So key differences to look out for: the relationship, the linear relationship you're not looking for is, you're not looking for the relationship between dependent and independent variable. Rather, you're looking for a linear relationship between the link function and the logit model, which new terms, but basically same thing as I was saying here, log odds of your dependent variable. Next, it's actually the way the model is fit is slightly different. It doesn't use OLS. It uses maximum likelihood estimation. I'll talk a little bit as to how that works later. And I will also sort of do a mini revision of what MLE is. And finally, errors, they have to be independent, but they don't have to be normally distributed. So that's one thing that you don't really have to look out for. You don't need to look out for your heteroscedasticity. You don't have to look out for your QQ plot with logistic regression. All right, any questions before I talk about the algorithm? All right, so logistic regression is kind of abstract because you're doing a lot of mathematical transformations. So first, what you're doing is, imagine in a logistic regression problem, your y-axis and your data points. Let me get my annotator real quick. Your data points are not going to be like scattered around in the scatter plot like how a lot of our linear regression data sets look like. Our logistic models data sets are going to look a lot like this. You know, you have a lot of points at the zeros and on the ones. They're all going to be either 0 or 1. So they're very likely going to be something like this. So obviously, if you just try and fit a straight line through that, it's not going to be very accurate. Your R squared is probably not going to be good. You're going to have crazy RMSE values. The RMSE values are going to be literally the distance from like the 0 or 1 line to whatever regression line you fit. So technically, yeah, you can try and fit, you actually can throw this data into a linear regression model and get some coefficients, but it's not going to fit very well. So instead, what you do, instead of trying to fit this straight line, you're going to fit this S-shaped curve. And this S-shaped curve is shaped like this for two reasons. One, it hugs the 0 and the 1 very tightly. So overall, you know, the distance from your points to the lines will be smaller. With this like S shape that kind of goes through the middle, that accounts for points that are a little harder to classify. You know, you can sort of imagine, just like mathematically in space, points that are around this area and around this area are going to be easier to classify, just mathematically easier to classify. But here you might have some that, you know, are in the middle zone. You're not too sure whether they would be zeros or ones. And that's kind of the purpose of having this S shape. It basically allows some leeway for certain points to maybe have higher or lower probabilities for the other class. So we're really constructing this S-shaped curve, and that is a sigmoid function. Questions so far? All right, so the general idea is we want to fit this curve. And the way we get this curve is actually through a lot of processes of transforming this curve into a different straight line, back into a curve, back into a different straight line. And they're doing this gradient descent of fitting the best curve through MLE. And if we don't remember what MLE is the whole idea of trying to fit the best distribution to our data. MLE, usually you have some sort of hypothesis on what kind of distribution fits our data. Like if you remember the example I think I talked about was like the weight of puppies. And I had this hypothesis that the weight of puppies is going to be normally distributed, but I don't know what the parameters of my normal distribution will be. Like I didn't know what mean and what standard deviation I would use for that normal distribution to describe the weight of puppies. So in a similar manner, they're trying to see, all right, which sigmoid curve is going to fit the data best. So what it does is it adjusts the parameters of this sigmoid curve through gradient descent and figures out the best way to fit most of the lines. So sigmoid curve, the best sigmoid curve might not look like this. The way it transforms is sort of can define how the slope of the S, the middle of the S. So different sigmoid curves, one might look more like this, it might look more like that. And not only that, after doing that, one other thing you can adjust is also the threshold, or where do you round your values. So by default, let me get my pen out. By default, you would want to say, all right, below 0.5, we're going to classify as 0, above 0.5, we classify as 1. Something else that you can actually adjust is instead of 0.5, maybe I realize that I'm misclassifying a lot of these points. Maybe I want to focus on, what is it, false. I want to get rid of my false positives, false negatives. And so therefore I change my threshold to here, just so I don't misclassify any of these points. That makes sense. So it does depend on your context again, which is why I think it's always important to define like your problems in context. It does depend on context what you want to do with your threshold. And I'll talk about more implications of that later as we talk about evaluating our classification models. But any questions about that so far? All right, so the idea is we're just trying to fit the best curve to our data points. Ali, I think you were just about to say something.
The order of these data points are important?
The order is not important. The order of the data points are not important because similar to linear regression, the order of the data does not matter. It considers all your data the same, with the same weight.
Okay, thank you.
You're welcome. Anything else? All right, so here we have a little bit of math just to explain what's going on. When you have your coefficients, oh, actually, no, before I mention that, why we talk about log odds is because when you're doing this transformation, your y is actually also being transformed because we're trying to fit a line and the curve at the same time. And we're looking for these somewhat linear relationships. The linear relationship comes in with this function here, this logit function. It looks like that. And the purpose of that function is this function bounds your y values between 0 and 1. So as you're transforming between, curve and line and curve and line, the line, as you can see, has no bounds, right? This line can go very negative, can go as positive as it wants. But with this curve, any line that you transform into that curve, it will be bounded by 0 and 1. So this orange line will never go below 0. This line will never go above 1. If anyone's more familiar with math, those are asymptotes. So that's why you can sort of, in some way, you're fitting a line through your data with transformations, but how you make sure that your predictions don't go below 0 or above 1, you use this specific function to transform your y values. So I don't think that this, let's talk about this example. So when you have your linear regression, actually, let me see if there's a better one. Here we go. So this is actually what your linear regression formula will look like. Because this is what's going to be linearly related to each of your variables, your coefficients can be interpreted like this. So in exactly the same way as linear regression, a 1 unit increase in, for example, x1 will lead to a beta 1 increase in the logit of y over 1 minus y. Another word for this is log odds, if you ever come across that. Questions about this so far? So From this, usually, what you want to predict is y, exactly y. And so once you do, let me see, from here, let me see if I have this here. Great. All right, so from this equation, you can actually rearrange this such that the y is isolated on one side, and you end up with this equation. So not super clear here, but let me see if I can zoom into this specifically. If you want to get your exact prediction for y hat, and y hat will be between 0 and 1, you're actually plugging your beta and your x values into here. Oops. Plugging in all your values into this exponent over here. And that's really just a transformation of that linear equation. And these are the parameters that you get from MLE. Cool. Other questions so far? Again, I do think it's not as important to fully understand like the intricacies of how this works. Again, like if logistic regression happens to be a model that you want to hone in on, and to be honest, out of all the models, logistic regression is one of the lesser preferred ones by students, just because you have all these linear assumptions to keep track of, and the other ones actually don't. If you are interested in getting into logistic regression, I will send out a bunch of resources after study group today. But yeah, before I get into like the coding and classification models, other questions?
Just real quick, in that formula, what does the E represent?
Oh, that's a great question. E is like is one of the mathematical constants. So E is actually evaluated, so I think 2.17. It's a constant about 2 point something. And E is a mathematical constant, similar to like pi, where it's used as a constant, and all you're doing is you're raising E to the power of like negative all of that. But yeah,
Thank you.
that is what E is. You're welcome. Again, I really think those StatQuest videos explain it very well, and it actually has like really cool animations of how the line is being fit. So highly recommend that if you want to see that. All right. Okay, so coding logistic regression. So this section, we're going to be talking about, the different syntactic things to keep, to just be aware of. Syntactically, logistic regression has very, very similar syntax to all of the other models that we'll be talking about, which I think is pretty neat because you learn one, you can sort of implement them all, which is why for your projects, most of the time people will just like implement every single algorithm we talk about, and then, as I suggest, just learn like one, maybe two. So let's get into this. Some of the new things that we're importing here, we're going to import data sets, and I'll briefly talk about what that does. And here we're importing our logistic regression. And here we have a normalizing scalar. Let's import all our stuff. Data sets within scikit-learn, if you're just looking for a quick data set to like play around with or just like practice implementing something, scikit-learn actually has built-in data sets. And I'm going to be using one of them. I think they have like, I think the car data set can be found in here. I believe they have like a wine data set that talks about like alcohol content of like wine quality or something like that. So if you're ever looking for a data set that you just want to like play around with, that's an easy way to get it. You don't have to download anything. You really just have to import data sets and load specific ones. So what I'm going to load now is this iris data set, which is just about flowers, like irises. And this is a pretty popular classification data set with 3 kinds of irises. So let's just load this data set up. Here you can see that here we have the sepal length and width, petal length and width, and this is our target. So target, I just did the head so you can see that they're all 0, but with value counts, you can see that there are 50 values per class. And what we're going to do is we're going to see if we can use these 4 features to correctly predict whether it's iris 0, iris 1, or iris 2. Some other versions of the data set have the actual name of the iris, but I unfortunately don't have that here. So any questions about like the setup of our problem? All right, so let's just first look and see what our data looks like. This just really quickly to do EDA for classification problems, where previously, we were plotting a lot of scatter plots against our dependent variable. One way to look at it is this. This is also a scatter plot where you're plotting the distribution of your variables across each class. this can also be shown as a box plot. One that I actually really like is overlapping histograms. So basically you would have, for example, if you had a continuous variable across two classes, I would just, something that I like to see is just like overlapping histograms to just see like the distribution of that variable across the two classes to see if they're different. And usually if you can see like, you know, a difference in the distribution of each class, it's typically a better predictor. You can see here, it looks like sepal length is kind of obvious, like 0 is around 5, 1 is around 6, 2 maybe around 6.5, a little bit of overlap there. This one is a little more separated, but yeah, to do EDA for classification projects, procedurally about the same as we were doing with regression, but it'll for sure look kind of different. So just a super quick EDA because we only have 4 features here. Same thing, we're also going to do our train test split. So here we're just splitting it up. And again, something I'm not sure if I mentioned earlier, all of these algorithms are all going to be in scikit-learn, with the exception of one that I'll talk about. I think that'll come probably next week. But with the exception of one algorithm, they're all in scikit-learn, which is great because that means they all have the same syntax, same way you fit and predict your model. So here what we're doing is we are instantiating our logistic regression. And remember yesterday with regularization, I talked about hyperparameters. We were adjusting our alpha for different amounts of regularization with our ridge and lasso. With logistic regression and other models, you have a lot more to tune. I'll get more into tuning. Logistic regression is not a big one that people really deal with tuning, but other models that we will talk about next week do. So these are just all of the hyperparameters that you can use for logistic regression. And just to show that the syntax is the same, we'll just fit it to our train set. It pretty much looks exactly the same as we did with our scikit-learn linear regression. Here you can see we get our y-hat train and test by using our dot predict function. And let's just take a quick look at our y-hat test. It's just going to be an array of 0s, 1s, and 2s for like what the prediction is. So pretty straightforward. That's what it is. Just before we get into evaluating classification models, which is going to be applicable to all the other models we're going to talk about, let's just take a preview of our results. Previously, we talked about RMSE, but here we can't exactly do that because the difference between the class numbers doesn't really mean anything. So if something was like a 0 instead of a 2, you wouldn't say that that's like an error of 2, if that makes sense. But we can first of all see how many values were correctly predicted. So here I'm really just looking and taking a look at, with our y train and a y-hat train, how many of the values match. So y train were our actual values, y-hat train came from our predict. So out of, I think, out of 120 values, 3 were misclassified. So 3, even in our train set, were misclassified. And then in our test set, out of 30, we have 2 that were misclassified. And this is just like a really quick way to do this. Very likely you would not have this exact code because we're going to talk about some other ways to evaluate models. But questions about this process so far? Cool. Should look kind of familiar, just slightly different. So for classification problems, we have a whole nother set of evaluation models. Not evaluation models, ways to evaluate your models. With our linear regression, mainly we were looking at RMSE, we were looking at R-squared. Basically says how well is your model fitting the data, and also how good is your model at predicting. For classification models, that looks slightly different. Some of this might look familiar if any of you have seen, I think, statistics. This is actually quite common to see. And we also had talked about the idea of like false positives and false negatives when we talked about our hypothesis testing. So some of this might be familiar, but I think this is more grounded in the context of classifying your data. So the first thing we look at is we can actually look at a confusion matrix. There's a built-in function for that, which I'll show you in a bit. But a confusion matrix is a very, very visual way to show you how well your model is doing at classifying. What a confusion matrix looks like, it usually looks like this. These 4 boxes are the main part of it. Let me just like highlight that. These 4 boxes are the main part of it. literally will tell you how many true positives, how many false negatives, how many false positives, how many true negatives were in your test set, or even in your train set as well. And from these numbers, one, you can literally see like, all right, how many points were misclassified on these squares and how many were correctly classified on the other two. From these numbers, we can also get more aggregated metrics. And so the metrics that we have here are accuracy, recall, precision, and F1 score. So these are the formulas. I personally always mix up precision and recall. But overall, accuracy is telling you how many were predicted correctly out of all of your points. Recall is your true positives over, and actually let me clear all of this here so I can make this a little bit clearer. Recall is your number of true positives over your actual positives, over the number of actual positives. And then precision is the number of true positives out of your predictive positives. So because of this, and you can sort of see that it's taking a different part of the confusion matrix, recall is usually more sensitive to false negatives, and precision is more sensitive to false positives. So again, depending on your context, you usually will prefer one over the other. And if you do prefer one over the other, maybe instead of looking at overall accuracy, you might take a look at recall, you might take a look at precision. And then finally, F1 score is an average of recall and precision. It's not your conventional average, it's actually more of what's known as a harmonic average, but this is what the formula looks like. You can sort of see it's kind of similar, but it's pretty much an average of your precision and recall. Questions about this so far? This is a bunch of new information. Typically for every single classification model that you run, it's a pretty good idea to output your confusion matrix and your aggregated metrics. So your accuracy, recall, precision, F1 score. All right, just as a quick recap of what these do, I think I pretty much mentioned all of this. Accuracy will take into account both false positives and negatives. The con is it can be misleadingly high when there's a significant class imbalance. So we haven't really talked about what class imbalance is, but you can sort of imagine, let's say I have a data set that I'm trying to predict fraud. So fraud happens, but it doesn't happen to a great extent. So you can sort of imagine a data set of like 100,000 people, maybe like only 100 of them are cases of fraud. Just to make things simple, let's go with 1,000. So out of your entire data set, only 1% of your data is fraud, but you want to train your model to be able to detect cases of fraud. Some models like to take the easy way out. Basically what that means is, if you were to just predict that everyone is not fraud, you would still have an overall accuracy of 99% because you would just predict, everyone to be not fraud, the 1% of the people who are actually fraud misclassified, but still a pretty high looking number. So that's a case where a significant class imbalance means that you might not want to use accuracy as your metric. Does that concept make sense? Cool. So as I mentioned before, with precision and recall, again, depending on, you want to detect fraud. In the case of detecting fraud, would you rather detect fraud when it isn't, or would you rather say that things are not fraud when it is? So again, depending on the context, it might differ. So because of that, you might want to use either recall or precision. Recall is more sensitive to false negatives, precision sensitive to false positives. And again, as I mentioned, F1 score is some harmonic mean of recall and precision. There are a couple other metrics. They are, in my opinion, slightly less useful. Again, I'm going to say that this is my opinion. If you want to use these, please do. The other things that we can talk about are AIC and BIC. There is a very comprehensive reading on AIC and BIC in your lessons in this section, I believe. So I would say good idea to read through. It is a very probabilistic way of evaluating your model. So it could be interesting. Honestly, sometimes it could be a good idea to just print all your metrics just so you have more things to compare against. AIC and BIC was also one of the values in your regression output, if anyone remembers. And it just gives you some measure of how well your model is fitting your data, probabilistically. The next thing I wanted to talk about is ROC curves. So ROC curves basically is another way to show how well your model is at predicting. ROC curves plot the trade-off between your true positive rate and your false positive rate. You can sort of see that, all right, in a true positive rate and false positive rate, if you just think about what these numbers mean, ideally, you would like to have a 1 true positive rate, because between 0 and 1, you want 1 for a true positive rate and 0 for a false positive rate, right? You always want to correctly predict, not incorrectly predict. So ideally, what this should look like is you want this curve that plots true positive against false positive. You would want your true positive to be as close to 1 as possible, with your false positive rate being close to 0 as possible. So typically with an ROC curve, and again, there's one lesson that goes through like the calculation of it. I will say ROC curves is more of like a visual cue for how well your model is doing. Not many people one will use this as the defining metric for how well your model is doing. But also ROC curves cannot be used for every single model. And ROC curves also work slightly differently depending on what your problem is. And I'll actually have an example of that. So ROC curves, usually you can plot it out. There are built-in functions for it. Basically, it has if your curve is closer to the top left corner, usually better. A perfect ROC curve is one that literally looks like that. Imagine those are straight lines. That is what a perfect ROC curve would look like. All right, I don't think that's super important, so I'm gonna just skip over that. But yeah, questions about all of these metrics. I am going to do quick examples of each one. All right, so first with confusion matrices, scikit-learn has a metrics library, which I think we use them for like mean squared error last phase. So for this, all you have to do is give it your model, and this is the logistic regression that we had trained before. Feed it in your model and feed it in your X and Y. So what it'll do is it'll run your data through the model and show you how things are classified. So I did it for both the train and test set. So I think confusion matrices, very, very visual, very easy to see what was misclassified and what are things to possibly look out for. So you can see here for our 0 species, everything was correctly classified, right? You have no true labels of zeros that were misclassified as 1s or 2s. On the other hand, there looks to be some confusion between 1 and 2 here. We have 2 of our 1 species that were misclassified as 2, and we also have 1 of our 2 species misclassified as 1. So probably in your modeling, in your future modeling, you maybe want to look out for those cases. And similarly for our test set, it looks like this. And same, you would interpret the same way. Pretty cool. This confusion matrix, I believe it actually pulls out of Seaborn. So this is a Seaborn chart, which is why you can use these values if you want to change up the colors. All right, other than the confusion matrix, really quickly, you also have classification report, and that gives you those 4 metrics of accuracy, precision, recall, and F1 score. And so with that, all you have to do for classification report is you feed it in your actual values and your predicted values of whatever your target is, and you can put your classification report. Pretty cool here. You can see that for each class, it tells you how well your model is doing for each class, which is pretty neat. You can see here that precision recall, overall your accuracy is 97% in your train set, 93% in your test set. You can see that, for example, you have a perfect recall score of your 1 class, and your F1 score usually is between your precision and recall values. So yeah, I don't want to go too in depth into these exact numbers, but depending on your case, on what your project is, you might want to take a look at these numbers more closely. Questions about this?
Yeah, would you be able to tell us what the weighted average
Mm,
means?
mhm. The weighted average, in this case, it's not very different for, so these are the weighted average accuracies. So it basically takes like your data points within your weighted average of, oh, sorry, it is looking at your weighted average across the different classes of precision. So your weighted average of precision is about 0.98. And because these classes are fairly balanced, your weighted average for precision is 0.98. If that makes sense. And then macro average is a different way of calculating average. It's just a different formula. I honestly don't remember off the top of my head, but it's just another average. But yeah, weighted average. If you had, like, for example, a majority class of 0 and a minority class of 2, meaning that like your data set was heavily skewed to 0 values, this weighted average, for example, would be closer to 1 than to 0.95. Anything else? All right, we are just at 3 o'clock, but there's one last thing I want to talk about, which is the ROC curve. So one thing that I conveniently did not mention was that ROC curves are telling you the trade-off between true positive and false positive rate. Now, this data set that we were working with has 3 different classes. How do you know which one is the positive? How do you know which one is the negative? And how can you plot that on an ROC curve? So the way that you get around that is you do a 1 versus all approach. So it actually is going to, the right way to do an ROC curve if you have multiple classes is you would actually plot a single curve for each class. And what that looks like is, and here you can see you can import your ROC curve. And then you would have to do this pre-processing step. I won't go into that too much. Honestly, it's something that I, as a student, copy and pasted and figured out later. So I think that's something you can also do. But with that, what you would do is your curves will sort of look like this. And this is with our test set. And for our test set, this is how we would evaluate this. This line here, and this is our, I guess both our class 1 and class 3 lines are perfect, have perfect ROCs. So if you remember, both our class 1 and class 3s, wait, I believe, let me see which one it's using. It should be this one, I believe, that they're using this data set. Yeah, that both our class 1 and our class 3, and in this case it's 0 and 2, were, I believe, perfectly predicted. I think they might have mixed this up. But anyways, here you have 1 and 3 being perfectly predicted, and then 2 is not perfectly predicted. And for each line, it's taking, like, for example, for this red line, it's taking 2 to be the true positive and everything that is not 2 to be the negative. If that makes sense. So that's how you deal with like true and false in a multi-class situation. But yeah, usually like the more classes you have, ROC curve just becomes harder to read, which is why it makes more sense to either one, look at a confusion matrix or just take a look at your overall metrics. One final thing to mention about this is that instead of this classification report, it is actually enough to use the straight up precision recall, F1 score, and accuracy of the model. This one breaks it down. This also does kind of like a 1 versus all approach. So something you can do, you can actually from sklearn.metrics, I believe they have accuracy, they have the accuracy, recall, precision, F1 score, all within there. As long as you use those metrics, it's acceptable as well. And those are, I believe that is the code that you'll see in your labs. But this classification report just goes into a little bit more detail. Cool. So before I get into that, I wanted to talk about this ongoing mini project that we're going to be doing. I know we're a little over time, but this is usually feelings time anyways. But for your working groups that I've set up for this phase, and again, if you haven't set up your working groups, the groups are on the homeroom, and I did say that the first person in each list is going to be the one in charge of setting up those working groups. So if that's you, please do that. So for this ongoing mini project that we're going to do for the next 2 weeks, I have this data set here, and I'll send you all the CSV on Slack as well. With this data set, of course, look into like what all of these columns are. We're going to just implement all of our classification models. So what I want y'all to do is, I think the best way to do this is for you each to have your own notebooks, import the data set, maybe talk about the cleaning. You can totally do cleaning differently just to see how different methods of cleaning and transforming will affect your model's performance. Really up to you. My main goal for this is just so everyone gets used to implementing and evaluating classification models. So take this data set. One thing to note is that this default payment next month is what you're trying to predict. This data set is trying to predict if a person is going to default on their next payment or not based on their pay history. So hopefully what I want you all to do is to each have your own notebooks, import this data set, do a little bit of cleaning, and since we already talked about a logistic regression model, just implement that. It's not going to take very long. You can copy and paste code and just take a look at your evaluation metrics. As we learn new algorithms, and we're going to pretty much do a new algorithm every study group, just keep on adding to that notebook and implement all the other algorithms. And then you will be able to compare, like, all right, on this data set, what model is working better? Things that you can do to make it more interesting. As I talked about with logistic regression, there are a bunch of different hyperparameters that you can use. So maybe look at the documentation, maybe like adjust your hyperparameters. Maybe you can decide, all right, I'm going to try this. Maybe someone else try that just to see how it performs. But the main idea is to get used to implementing these algorithms and evaluating them. So hopefully when it comes to the project, the procedure will be, you will have the procedure down. But yeah, I will send out the data set plus instructions written up. So yeah, any other questions?
In the class of logistic regression, we put the C equals to 10 to the power of 12.
Yeah.
Which means that we are not very strict on regularization, right?
That's right.
So
that is
it's
right.
not important in this case?
You can actually introduce regularization in here. Again, depending on like whether your model overfits to begin with, would be something that you use to determine whether you're going to regularize or not. So with that data set that I'm going to send out to you, maybe you have an overfitting problem. And if it is, you would adjust C down. That's something that's kind of irritating. I know I was talking about like regularization and the inconsistencies. I was scrolling up and down to see if I have the documentation linked. But something that's inconsistent here, you can see that C here is 1.0, and C, if we look at documentation, is the inverse of regularization strength. Why they do that, I don't know, because we talked about regularization in terms of alpha before. But yeah, some models have it as C, some of them have it as alpha. I don't remember if there are any other Greek letters that they use, but yeah. So just take note that smaller number equals to more regularization. So the default is 1. If you divide it here, we're dividing it by which one is that? Yeah, we're dividing it by, I think, yeah, 10 to the power of 12. So that would be an inverse of that. So we're actually introducing regularization here. No, wait, yeah, inverse of that. So yeah, that's something that I want you all to work on as you go on. At like every few days, I will be asking for just an overall summary of like your models so far. And that would be something that I would like to see you all, or I would like you all to be talking about. Just like how well your models are doing, how different parameters are working with your data set. And yeah, I'll send it all out to your Slack channel. But cool, any other questions to close out?
Yeah, I have one. I was trying to follow along with the study group notes and I got a bunch of errors. It wouldn't import the plot confusion matrix. I don't know if your study group notes are more up to date than mine and I just need to download them.
Ooh, okay, with the plot confusion.
Things are out of order.
Yeah, that also could be that. Yeah, the one that's on there is something that I updated only like a month ago. So that could be it. I'll send out this version too. I'll upload this as like you'll see an updated notebook. So I'll have that. One thing that could be throwing it off, the confusion matrix is in a newer version of Seaborn, I believe, that you guys don't have. I don't remember if it was with your cohort that I walked through how to update something in your learn environment. That could be something that you look into. I'll look for the video and I'll link it when I post the recording for this as well. But pretty much, I think if that is your issue, the confusion matrix, you just have to update the version of Seymour, and that's in the Learn environment, and that hopefully will work.
Okay.
Awesome. Anything else?
I have another question.
Yeah.
For accuracy, I mean, accuracy is considering both train and test of our data, or just the train?
Yeah, that's a good question. So with so it depends on what you feed it in, what you feed in. So the way that if you were to use like scikit-learn accuracy score, and this is something that you can import as well, with accuracy score, you just give it the actual values and the predicted values, and it'll just calculate the accuracy based on that. So you can either give it your Y train, Y hat train, and your Y test, Y hat test to get like separate train and test, but also, I mean, I don't know why you would do this, but you can also just give it all of your Y values and all of your Y predicted values together as well. So yeah, because those are what it, yeah.
In our example, the support point for accuracy was more than the others.
Oh, is it, are you talking about this? Let's see, this number here? So support, support is really just how many of the data points are in that category.
For accuracy, it uses 120, and for other, use less than that.
I think, I think this is just because this section down here is an aggregate of what's up here. So I think the 120 is probably what it's aggregating. So I don't think 120 is accuracy. I think it's 97% out of 120 data points is probably how I would look at it.
Okay.
But yeah, that is kind of confusing now that I look at it. But yeah, 120 is just the number of data points that you have. All right then, any final questions? Cool, I'll write up all the instructions that I want y'all to do for this phases mini project and send it out so you have that. I'll also put it on the homeroom. Cool, so as usual, because it's Friday, I'm gonna stop recording and we'll get into our feelings. Let me stop this.